Step one.
FTW.
What do we got? Oops. This is.
Yeah, so too. State of the Union.
Yojo.
State of the Union. Yojo.
Yojo.
Assigning variables.
Assign symbols to all given.
Ah.
I have an English quiz today.
Okay, so first things first. What do we need first here? Variables. Variables. We probably need a picture. Well, I mean, we don't really need a picture on this one, but it's easy enough to get a little sketch just so we can kind of orient ourselves. Not necessary. What is this graph going to look like? Upside down parabola. Where's the vertex going to be?
Four.
It's going to be, 0, 4, right? Okay, good. So,
How'd it go?
okay, so it's going to look kind of like this. Where are the x-intercepts going to be? What are the zeros of that thing? Positive, negative 2. Good. So it's going to look like that, right? So if we're trying to find the place, or you can probably see it's going to be places closest on the graph, closest to the point 0, 2. And I didn't draw that very symmetrically, but it should be symmetrical. Right? And so we don't know exactly where it is, but it's somewhere probably kind of in here-ish, right? Agreed? It's not going to be clear down here, obviously, right? Someplace up there above the x-axis probably, right? Okay? We'll find out, though. Okay, so what are we going to do about this? You got your recipe sheet here. Step 1 says we want to assign symbols to all the variables. Make a sketch. What are the variables going to be? Okay, x and y, how about? Sure. We don't know where these points are, right? In fact, we don't even know how many points there are. But the math gods will tell us that if we just solve the equations. We're just going to maybe call this point right here. That's going to represent the closest point, or points if we get multiple solutions. And being as we're on the coordinate plane, really the natural choice would just be x and y, right? We know the coordinates of this point right here. They're 0 and 2, right? Okay, now what is it that we're trying to minimize or maximize? Because that's our primary equation, right? So step 2 asks us to always build a primary equation. What is it? It doesn't come out and say, it doesn't say minimize or maximize this quantity, but what could we infer from that? What do you think? What are we trying to minimize or maximize? Or at? Distance, sure. We're trying to minimize distance, aren't we? Right? Okay, so then this would be distance, right? And what's our primary equation going to be? Yeah, right. It's going to be the distance formula, which is just Pythagorean theorem, so you do know it. Okay, in fact, I'm putting you on the spot. What is it? What's going to be the distance between those points?
You said Pythagorean theorem?
Yeah, that's all it really is.
A squared plus B squared equals C squared.
Okay, so what's a squared, what's b squared, and what's c squared? Because here's our, I mean, this is our triangle right there, isn't it?
Yeah.
Right?
So
Oh.
it says the hypotenuse, it says the distance.
Okay, so distance squared
Distance squared.
equals,
A is the 0, 2.
well, those are the coordinates of that point.
Yeah.
Right, so we need to know the length of that leg and the length of that leg. Now, we don't know them.
That's
Right.
x squared plus y.
Well, we're going to write them in terms of x's and y's probably, right?
Yeah.
Now, but it's not just x squared plus y squared because we're not starting from the origin.
No.
Right? What's going to be the change in x is going to be what?
So 2
So it's going to be,
times 1.
we're going from x equal, we're going to go from a value of x to a value of, no, 0, right? So that one is just going to be like x minus 0 squared.
Oh, okay,
right?
yeah, that's what I thought. Okay.
So that one's just plain old x squared. Now what's going to be the length of the vertical length there. Y minus 2 squared, right?
Well, are we
Because it's
using,
starting 2 above.
are we getting that from the point,
The back of that.
0, 2 point?
Yes, right, 'cause we're trying to find the points, the point or points closest to that point. It's all on this graph, the points closest to that point, right?
Okay.
So is everybody okay with where we are here so far? Does that make sense? And that's just distance formula, right? We know the distance equals the square root of, we just haven't square rooted it yet. X2 minus X1 squared, right? Plus Y2 minus Y1 squared, right? Remember that? Okay. Okay, so then, do we want to square root this? Because we're trying to minimize distance.
I don't see it like it, no.
Maybe why not?
It'd get complicated.
It'd be complicated, yeah. Okay, and does it make sense logically that we're just trying to find the point that minimizes the distance, but if we could find the point that minimizes something else that's gonna give us the same answer, why not use that? Does that make sense? So we know that when we find this point, it's gonna minimize d, but if it's minimizing d, wouldn't it also minimize d squared?
Yes.
Does that make sense?
That makes logical
That's-
sense, yeah.
And so we can avoid having to do that, having to mess with the square root there then, at least for a while, right? So let's how about if we call this, instead of a small d, we'll call this capital D. Capital D is gonna be our distance squared formula, which is not really what's being asked for, but it's actually not what's being asked for. We're not asked to find distance, are we? We're only asked to find the coordinates of the point or points. And so we've just chosen a different function that's also gonna give us the same answer. Okay? Questions on that? Okay? So there's our primary equation. I'll rewrite that so it's a little cleaner here. We got d equals x squared plus the quantity y minus 2 squared. What's next? Yeah, do we need the secondary equation here? We do, don't we? Right?
Yes, we do.
We've got two independent variables, x and y, so we need we need an equation of constraint. If there are no constraints, we would just put the point right on top of this one, right? And it would be kind of a senseless problem. But there is a constraint. Think of this as a bead on a wire. What's the constraint here?
Okay, can't go off the wire?
Yeah, it's sliding on the wire.
Yeah.
Okay, so the wire must be the constraint. And the wire, by the wire we mean this parabola, right? So what is our equation of constraint then?
4 minus x squared.
Yeah. It's actually given to us. Here's the equation of constraint, right there, because that gives us the shape of the wire that the bead is sliding on, right? Okay, does that make sense? Now, isn't it kind of cool that you can look at it that way? You can say, okay, I mean, without a constraint, it doesn't make any sense. It'd be, right? But with a constraint, what is the constraint? You can kind of look at the problem and say, well, what's constraining this is the parabolic wire. And so that's got to be the equation, right? That points us right to the equation of constraint. Okay, so what's next?
Gotta plug 4 minus x squared.
I want to put a box around that. Okay, plug it in. Good. So I'm going to plug all this stuff in to there, right? And I'm going to get my new primary equation of a single variable. So now we're going to get d equals squared plus, instead of a y, we get a 4 minus x squared minus 2, which becomes what? Squared. You're right. So if I combine like terms in there, so they just give me, what, 2 minus x squared? Okay, so let's try to turn this all into one big equation now. So we get d of x equals, what's all this stuff going to be? If I take, this is going to become a 2 minus x squared squared. If I expand that out, what do I get? And do you remember the expansion formula for a binomial?
Yeah.
Because this is pretty useful.
Oh, yeah, I got it.
If we have something like a plus b squared, what's that expand to always?
A squared
plus AB.
Plus
Plus
2AB.
2AB.
Plus B squared.
Plus b squared. Good. Okay, so we can do that trick right here, can't we?
Yeah,
So that's a is 2, b is negative x squared, right?
yeah.
So we get what? 4, good. Minus 4x squared plus another x squared. If we add it to this one outside, is minus 3x squared plus x squared squared 2x to the 4th. Okay. All right, so there's our function. Okay, now we can just do our calculus. All that work was just to get us to the point where we could make a table, do our calculus and make a table, right? So we do need to know what's the domain here. Well, this is not so much a physical problem, it's kind of a mathematical problem in this case, right? Are there any, what values of x could be considered in this problem? Are there any restrictions on x?
No.
So our domain is all reals.
All right.
We're gonna come up with some answers that are, yeah, we'll get answers, right, but there's nothing excluded. So now we'll do calculus. This is what we're good at. Now what?
Say that for yourself.
The
Differentiate.
table.
Okay, the table. So to build the table though, what do we need?
First,
Differentiate, good. So d prime, first derivative is what?
minus 6x.
Yeah, we'll rearrange it when we differentiate. So let's do this one
Okay,
first.
4x cubed. Minus 6x.
Okay, so there's our first derivative. And it's so easy to do here. We've got a polynomial, so we definitely want to do a second derivative.
Yeah.
It's really simple.
Hell yeah.
So our second derivative
Double prime.
is what?
12x squared minus
12x squared minus 6. Good. So let's go ahead and find the critical numbers of the first derivative. Do we need critical numbers of the second derivative here?
No.
No, we're not. All we're looking for minima and maxima, right?
Yeah.
So where this is nowhere undefined, agreed?
Yes.
D prime equals 0 when?
When x is 0.
Okay, yeah, so we're gonna, I guess we need to solve this now. When we set
Well, maybe.
4x cubed minus 6x equal to 0, what can we do to solve
Factor
this
out
equation?
x.
Factor out next, in fact, we can factor out a 2x, leaving us with 2x squared minus 3. So what are all of our zeros gonna be then? If we set those factors equal to 0 and solve, we get x equals 0 from this factor. And then square root of 3/2, but plus or minus, right?
Yeah.
We'll add the 3 to the other side. If we set this, what we're doing is, if we just take this factor right here and set it equal to 0, then we can add the 3 to the other side, divide by 2, and get x squared equals 3/2. So x would equal plus or minus the square root of 3/2, right? So those are our 3 critical numbers. Okay, make sense?
Yes.
All right. And now we just need to make our table, don't we? Okay. So can you, if I draw that, can anybody see that? Put it on the bottom.
Yeah.
Okay, so we get our critical numbers of minus square root of 3/2, 0, positive square root of 3/2. Those are all zeros of the first derivative. And so what do?
Find the sign.
Find the signs, yeah. Okay, so if we check the signs of the second derivative at a positive value, square root of 3/2, let's see, that's that's gonna be bigger than 1, isn't it, right? So a number bigger than 1 squared times 12 minus 6 is clearly Same thing if it were negative because I'm squaring it, right? Okay, what about at 0?
It's negative.
It's negative. Okay, so then we know what we got here. We've got a relative, this is gonna be a minimum, right? Because it's happy. That's a minimum, that's a maximum, a relative maximum. So, what do we find? What's the answer? Those are the x values at least, aren't they? And if they want the points, what's the only thing we'd have to do? Yeah, just plug it into the original function to find the y values, right? Make sense? Okay.
We plug it into the bottom.
We'd plug it into, yeah, up here, right? Into that one, yep. Or this, I guess we have it right here, yeah. Yeah, the equation of constraint, that's always where we go back to get the other variable. Okay? All right, questions? Okay, let's look at a different kind. What about one like this, where we have to actually draw a picture, kind of a physical one?
What's a story problem?
I'll let you think about that for a second.
I'm just gonna write the whole problem down.
Plug the x cube back into
Tell you what, would you like me to just print these notes out at the end for you?
Yes, sure.
Okay, I can do that.
Oh, dude, you can print it out. I don't have to write that.
12 feet, alright, that's gonna be a little longer than the pole. So, we'll measure it right here.
Fair enough. It doesn't have to be to scale, that's fine. Just drawing.
That's very shocking.
28. What else is there? 30 feet apart. Okay, right there.
2 wires attached to a single stake built at the top right here.
Single stake.
No,
In the middle.
No,
in the middle. It's in the middle.
Oh, it's supposed to be in the middle?
No.
Yeah, it must be a single stake.
I'm kind of enjoying this.
We got time. Alright, where? In the middle.
No,
in the middle between the posts.
That's
a goodie. Go
So
straight
like
in the middle.
that, and then like that.
It's just like the other
Yeah.
problem.
To the other pole.
It's just like the other problem, right in the middle. Between
Draw a
Right
little
here.
sign.
Yeah.
Okay.
That's where the stake is.
What, you guys gonna criticize my work?
I thought it was the Mona Lisa.
Better than I would do.
I don't know.
We browse those to draw.
And then I have to figure out like.
So we're trying to figure out, yeah,
And the moon,
right.
it's a question mark.
It's a 7. It's a 7.
Okay, very nice. Okay.
You missed the stake. It's not really ground. It's a stake.
Good job, that was good.
You gonna charge me if I want to get a print out of that and frame it?
That'd be
It's original.
cool.
That's original. Campbell
I
Agee.
can sign it.
Sign it.
Real quick.
In the corner. In the corner.
Question.
That's what I'm talking about. Here we go.
Nice.
We kill it.
That's gonna be worth something someday.
I like it.
Okay, so we got our beautiful picture here. We need some variables. So who wants to take care of some variables? Who wants to add the little variables? That's not so daunting.
Bam.
Anybody? Nobody. Okay, tell me where. Oh, all right, all right.
Oh, this is good.
Excellent.
Like that?
Sure, we could do that.
Okay.
Any suggestions on the variables?
That was what was missing
Okay.
right there.
So,
Wouldn't it be?
so we got it. Yep.
Could we do X for the bottom and then 30 minus X?
Okay, yeah, and we would have done that anyway because we would have had to have had an equation of constraint, right? And so to break this down to a single
Oh,
variable, we would have just probably used. So we could have done it either way, but we'll just call this y. We'll just call that 30 minus x because the whole thing's 30. Yeah, that makes sense. Okay. Now we got to come up with an equation. Okay. equation of, well, actually our primary equation, right? What is it that we're trying to minimize or maximize here?
Water.
Yeah, okay. And this is, we wanna use the least wire, right? So that's
Minimum.
a minimum, isn't it, right? And so what is that? We gotta come up with an equation for that quantity. If I were to draw that sort of that distance in purple, it's this whole thing right here, isn't it? That's what we have to represent, is that total distance. Okay, so how are we gonna do that? Yeah, Pythagorean theorem twice, right? What are we gonna get from the left right triangle? Because these are both right triangles.
Oh, I see. How do you know? Put it there at an angle.
Okay, so this distance right here is gonna be
Straight up.
square root of 28 squared plus x squared, right? Agreed?
Yeah.
It's just 30 minus x, right?
Well, and then this one over here is just gonna be 30 minus x, right? So when we do that, so this distance right here is gonna be square root of 12 squared plus
Quantity, 30 minus x.
30 minus x quantity squared, right? Does that make sense?
Okay.
Okay. And we got it in terms of a single variable already,
Yeah.
don't we? Okay, so we need to, let me write that down a little more neatly. So that, we'll call, once again, how about just capital D, right? So capital D of x is, what did we say, it was 20, square root 28 squared plus x squared plus square root 12 squared plus the quantity 30 minus x squared.
Bless you.
What's our domain gonna be? What are the values of x that we could consider here?
Positive measures.
Okay, what's the smallest value that would be in our domain? 0, yeah. Right, we could, we obviously we're not gonna do this, but we could make the wire go straight down here and then up like that, right?
Would be pretty.
So we- It wouldn't work, right? But it's, I mean, that would be the smallest value in our domain if we slid the stake and put it clear and right over there. What's the biggest?
The other way?
30, right? If we put the stake clear over here as far as we could.
So, could be closed, okay, gotcha.
Okay, but now we've distilled this down to, we can just shift out of, sort of real world mode and into just abstract calculus mode. And we're just gonna maximize, or we're gonna minimize this function on that interval. And so this could have come from section 3.6, right? This is just calculus. So we gotta do some, maybe we might wanna simplify this just a bit. Maybe, well, it's up to you, I don't care. I mean, we don't have to. We can just differentiate this the way it is too. Why don't we just simplify this
Okay.
radicand in here, whatever's inside the radical. One more step. This one's fine. Okay, so what are we gonna get here? 900 plus 144, so 1,044.
So
Yeah, that's what I got.
Wait, what?
Because we're gonna do 30 squared, so 900 and then plus 144. So then we get plus or minus 60x, right? Because that's a and b, we're just squaring out a plus b, and then x squared. Okay. Right. Good.
Yep, that's what I got.
Okay, so let's differentiate. What are we gonna get from that first term? How are we gonna differentiate that? Gotta think of the square root as being
1/2.
a 1/2 power. Okay, good. So that means we have a 1/2, right? 1/2 times this hand to the minus 1/2.
Yes.
What does the minus 1/2 really do?
Square root of the
Square root on the bottom, okay. So we could make this a 1/2 square root of hand times the derivative of hand. What's that? What's the derivative of 28 squared plus x squared? 2x, yeah, because 28 squared is just a number, so that's a constant. And so the 2's cancel. Okay, we good with that? Does that make sense?
So it's just X over.
So it's x over hand, yep,
Okay.
square root of hand, okay? We're gonna need the same kind of thing going on over here, aren't we? It's the same, it's just different, it's arm to the 1/2 this time, right? So we get 1/2 arm to the minus 1/2. So on the bottom, we're gonna get there's our 1/2, there's our 1/2, square root of arm. Times the square, or times the derivative of arm, which is
2x minus 60.
2x minus 60.
Oh, we
And we couldn't we factor a 2 out of that and cancel the 2's even?
Let's
Right?
do it.
Yeah.
So we could do that and make this instead an x minus 30.
Let's go.
Make sense? Okay, yes.
Why did the x squared minus 60s plus 1044 go on the bottom?
Because if we do, this is a 1/2 power. So the derivative of arm to the 1/2 is 1/2 arm to the minus 1/2.
Oh.
And so the minus 1/2, it just puts the square root on the bottom.
That
Minus
makes
1/2
sense.
power. Okay? Okay, so now we gotta find critical numbers, right? This is kind of an ugly looking derivative. In fact, let's go to the next page to find critical
Let's go.
numbers.
Save
Second
that, save that drawing.
Oh, I will. You give me a drawing, I'll give you a drawing.
Okay. Draw me something good.
Okay.
Thinking of a four-headed liger.
How about a Tygon?
What is a leopard? There's like a leopard and something else put together.
I don't know what that is. I've never heard of that.
No, like
I don't know. Wait, you're talking about a leopard? Like a.
Yeah, a leopard.
Yeah, a leopard lion?
Yeah.
Yeah.
Aren't they the real big ones? Which ones are
That's a
the-
liger.
Yeah, ligers are-
Ligers
Ligers are the big ones.
Yeah, ligers are big ones.
I want a liger.
Okay, so
With, yeah.
where's our derivative gonna be undefined?
Max equals 0, right?
It's gonna be undefined where? We got a couple red flags here, right? Because we know that there's 2 rules for real numbers. We can't divide by 0. We gotta worry about that. And we can't take square roots of negative numbers, right? So we gotta look at these and say, okay, first of all, could we get a negative number inside the radical there? No. Okay, now if we go back to this other page here, could we get a negative number? It's easier to see if you look at it this way. Could we get a negative number from that expression? You can't, can you? How come?
Guess not. Oh, because it's squaring it.
Okay, because this term is they're both being squared, aren't they? Right?
Yes.
So it's easier to see there, isn't it, right?
Yes.
Okay. Does that make sense? 30 minus x, even if 30 minus x is a negative quantity, because it's being squared, it's always positive, right? So there's no place where this is undefined. But where it could equal 0, right? And so we gotta, do we want to take a second derivative here, by the way?
No.
We don't want to take a second
That's a
derivative.
Let's do it.
No, we don't want to do that. But we could just use the first derivative test. If we set this equal to 0, that's kind of an ugly one, isn't it?
Yeah.
Okay, how are we going to take care of that one? I mean, we
Get the math gods to do it for
get the math guys to do it for us.
Yes.
Yeah, we got some options. We could try to write this as one big function on one side, right?
Oh, no.
It's possible, but why don't we just add this term to the other side and cross multiply?
Oh, yeah.
Or subtract it to
Much
the other
better.
side.
Much better.
Okay.
Yes.
So does that make sense? So then we'll keep this term on the left, so we get
X.
x over square root of hand equals minus this term. So we'll just make it a 30 minus x instead of x minus 30, right? If we subtract it over here, we get a -1 out front, which we'll distribute. Okay, make sense?
Yes.
Okay. Boy, I didn't think how ugly this would be. This is a pretty ugly one. Yeah.
This is long.
So if we cross multiply, yes, it does. We get x times. Okay, now what? What's the problem with that?
Too much.
It's too much. There's a lot there. What's really particularly ugly about that thing? Square roots. If we didn't have the radicals there, we could just turn this into a big polynomial and find the solutions of the polynomial, right?
Yeah.
But that's the problem, is that we have those square roots there.
Square roots.
So what do you do to eliminate square roots?
Square it.
You square both sides, don't you? Okay, but what you have to always be careful of, going back to honors algebra 2,
Every.
yeah, what do you have to be real careful about when you take both sides of an equation to a power?
Square and all.
Can't change
Yeah,
the signs.
maybe you have to worry about that too. There's probably lots of stuff to worry about. Let's look at a quick example. What if we had, I want to just reinforce this. What if we had the equation x equals how about this? How about if we had square root of x equals -2. If I square both sides, right,
Oh,
to solve for x, I'm going to get x equals 4. Okay, does that solution work? No. If I plug that back in, I get square root of 4 is 2, does not equal -2. Why did we get that non-solution? Because we squared both sides, right? Whenever you take both sides of an equation to a power, you potentially introduce extraneous solutions,
We gotta get into the eyes.
maybe non-solutions, right? And so so you always have, what that means is, the moral of the story is whenever it's a valid way, we have to do it to solve this equation. But when we're all done, we gotta check our solutions and make sure that they work in the equation before we squared it,
Gotcha.
okay, right? So if we square both sides here, what are we gonna get on the left side? And really, this isn't a big deal. This is just taking advantage of this property of exponents. If I have the quantity AB squared, or to any power, well, what do I get when what's the property tell me?
A squared, B
A
squared.
squared, B squared, or it could have been A to the M, B to the M, or something, right? So if I'm squaring this whole side, I've just got x squared times this square root squared.
Oh, jeez.
And that's no big deal, I just distribute the x squared, right? Okay, what about over here? I'm gonna get this guy squared, right? Which is, let's flip this around. So we're gonna get x squared minus 60x plus 900 from that squared, right, times that. Okay, so this is looking pretty ugly.
Yeah.
Maybe I didn't think this problem through well enough.
All right.
I have to start erasing.
So this side's piece of cake. This side we get just x to the 4th minus 60x cubed plus 1044x squared. This side, a little uglier. If I distribute the x squared all the way through, right? I'm gonna get x to the fourth minus 60x cubed. Well, that's good, we get some stuff canceling. Plus 900 x squared. What is 28 squared? I don't wanna really think about that. What is that?
20 and 20 is 400, right?
You can't just add them together.
What is it again? 784. Okay,
That's
so
not
then
400? What is it? 784.
784. So then if we distribute the 784,
Yeah, what was that?
I don't know.
784x squared, 784 times minus 60 is something huge. What's that? I don't want to do that. Okay, we'll do that in your head.
Which one is it?
784 times minus 60.
47,040.
Minus 47,040.
Oh, God.
74 times 6.
X. 47,040, right?
No, we can't. Wait, we're already too much invested.
Okay, and then we get this other constant. We get 784 times 900.
705,600.
Oh, sweet Lord.
705,600. Okay, but good stuff happened here.
A lot of good stuff and bad stuff. Wow.
Okay, that's good stuff.
Cancel
That's good
4
stuff.
things.
And so now, if we, let's see, we want to probably gather everything on this side, because we're going to have more x squareds on this side, right? Let's just trim this thing down now. So we've got,
Okay.
what did I just do?
There's too much information. Information over.
Your computer went full retard.
What did it do? I don't get it.
Never go full retard.
No, now you're doing your cross that. Whoa, yeah, scroll down. Scroll down.
Oh, scroll down.
No, you gotta cross off the 68.
Oh, there we go. Okay. Yeah, there we go. So I can go forward. There we go. Okay.
Let's see paper.
Okay, so we get 1,044x squared on this side is what's left over. Over here we got to add some stuff up. So this is going to be 1684x squared. So those we accounted for. Then we get minus that huge number, 47,040 x plus even huger number, 705,600.
Did you come
But-
up with this yourself, or do you have a problem generator or something?
This is, I just grabbed this one out of a book. So, which makes me wonder if there's not, I mean, I don't know, they must have solved it with a calculator or something. 'Cause I don't think they probably went through all this algebra. I should have probably looked, but that's all right, this is good practice.
Yeah.
So we'll just subtract this from both sides, and we get finally, 1684 minus 1,044 is 640, is that right?
Yes.
Yeah, we'll go with that.
So 640 x squared minus 47,040x plus, we don't even really care because the constant's going to go away when we, oh, never mind. No, it's not. We got to solve this, don't we?
Yeah.
So there's the equation we got solved. Yeah, I'm kind of hoping that all those numbers are divisible by 640. Let's just try it and see.
Let's see, right.
Is 47,040 divisible by 640?
No.
Are you kidding me?
Called it.
Oh, they can all divide by 10.
This is some BS.
Yes.
Straight up, just go ahead and say.
Divide by 10.
Oh crap.
All right.
This is fantastic math right here.
So we're going on page 45.
That's right.
That's right.
This is the way it sometimes goes. Okay, so we gotta solve that equation. Now, we could use the quadratic formula, but we're just gonna wait our hands a little bit, have somebody use their polynomial solver for us.
Right.
So Brian, that's you. Go to Polysmol 2. But we could plug this into the quadratic formula if we wanted to, right? We're not gonna try to
Oh
factor it.
God, no, we never.
And we could even probably try to like divide these all by 4 and then divide it by 4 again and whittle it down. But we're in the interest of time, we'll cheat it, but.
You just divide it by 10, yeah.
Yeah, we could divide everything by 10, that would help a bunch.
52.5 and 21.
Okay, so 52.5 and 21 we get, so x equals. If we went through the whole process of solving this, we get x equals, say it again, 52.5
Yeah, and 21.
or 21. Are both those valid solutions?
No, we have to check.
Okay, we got to check, first of all.
We have to go back.
Okay, but really, even after we check, we gotta go back to the original problem here, to that beautiful drawing. Say it again.
It doesn't fit.
Okay, good, the 52.5 is outside of our domain.
Uh-huh.
So the only one that we would need to check is 21, isn't it?
Yeah.
Okay? So we could go back then to our, where was it that we squared both sides? I guess that was about there. So if we put 21 in there, would it work? Okay?
Sure.
And
I'm gonna hope and pray.
anybody want to make a guess if it's going to work?
Yes.
Okay.
I'm gonna pray.
It is going to work. It is going to work. We know it's going to
What
work
would happen if it didn't work?
because remember now, this is just ARM, isn't it?
Yeah.
Right? Okay, I can guarantee this is going to work. And there's kind of a way around this algebra a little bit. It's nice to know how to legally cheat on this thing. So
Woo!
this is ARM. If I put 21 in there, would you agree that I'm going to get a positive answer inside the radical?
Yes.
Okay.
Yeah.
If I put 21 into this expression, obviously I'm getting a positive expression, right? And so the only way it wouldn't work is if one of those terms switched signs, like it did in my cheesy little example, right, where was it? Right there, right, where one side went from positive to negative. That's how you get extraneous solutions. So I'm gonna kind of because we're running out of time, I'm gonna just bypass that step of actually plugging the numbers in and checking. But we could easily do that, right? We could easily just plug all those numbers in to right there, and it would work, I promise you.
It works.
Okay.
I did it.
Oh, you did it, okay, it didn't take that long to do. So we found 21 feet away is where we place the stake. And then we get the minimum amount of wire, okay? Pretty good stuff.
Nice.
And we're saving
Wire's
money.
expensive,
We're saving
right?
money.
We saved the company probably $5 there.
For-
then-
For only 30 minutes of hard work.
If we wanted to figure out how much wire, like how long the wire was.
They don't just
How
survive.
long we do from there.